Good morning, everyone. My name is Balaji. I work as an expert or distinguished data scientist at Schaeffler. Have you heard about the term Schaeffler? Anyone? It's a European German company. We are specializing in high precision manufacturing, especially for aerospace and medical devices. We work in all automotive space. All the major automotive players are our customers here. I'm going to talk about high precision manufacturing today. Um, okay, so have you heard about Continental tires? How many of you heard about Continental tires? No? Okay. All right. So we own Continental tires. Good. Good. Thank you. Okay. Precision manufacturing. What about this? So precision manufacturing is all about the mechanical parts and or spare parts, kind of what runs behind the machines, like torque converters or your engine components. But it is for an industry that is like very specialized, like where the tolerance limits are very precise. The ISO standards, everything will be upscaled because these are the one that goes into your space shuttles or rockets or into your critical care medical devices. So that the industry is precision manufacturing industry. One of the key challenges is that the manufacturing process embeds a lot of quality control along the way, so you achieve very high precise products at the end. And even at the end, you need to verify defect detection at micron level, sub-micron level. So traditional cameras and things never works there. Okay, so what are the quality control challenges? So defect morphology, like even small micron scales defects with complex structures has to be picked up. And we need to adhere to strict ISO standards since it goes to aerospace kind of products. We have ISO or ITAR kind of governance happening over there. Surface finishes, even like in the smooth surface finishes, like minor scratches or pits that potentially can exasperate one into the OEM, into the products, that has to be picked up at the end of line. So all this has to be high precise, and even when you're doing inspection, that has to be handled at a very high throughput limit. Like you can't trade off your processing time for doing end of line inspections. So that brings out the automation challenges. How do we build automation challenges here? And also cost. These are the three different factors, right? So you need to be cognizant of about like what it takes to do an inspection process here for these kind of products. So currently it's about 15 to 20% of whatever revenue is. How can we bring down the cost at this stage? So for today's talk, I'm going to take two different use cases, how we handle high precision manufacturing defect detection here. One of them comes from aerospace, and other one is from the automotive, electric EVs. In the aerospace, we produce a lot of ball bearings. As you can see, these are all like ceramic or hybrid bearings, specialized bearings in going into aerospace. One of the challenges, like how do we detect these defects that's coming out of these balls, and some of them at a micron level. So, as I mentioned, ISO standard 3290 clearly specifies if you are doing surface inspection, these are the defects you need to pick up at this for this. And also, there are some approved methodologies like fluorescent penetrant inspection or ultrasonic inspections. And the resolution to pick up is like anything about 20 microns of a minor scratch that has to be picked up. And it is, if you look at it, FPI is the only approved inspection process. And FPI usually is a very expensive process. You can't embed them into a like kind of end of line workflow. So for example, you ship some parts to the customer, and then customer raises a complaint. It goes to an FPI mandatory process, which is a third party governed body, which will look at your whole batch and then come up with a statement like, okay, this has this defect, you need to go fix it. So it's a kind of a complex loop. Also, the standard mandates, like if you're using what kind of current methodologies? Current methodologies are using like stereo or fluorescent microscope. It's a manual process. People look through the microscope and then do the inspection. How do we automate this process? If you look at microscope, if you want to cover the area, it's about like 100. So you need to precisely rotate these balls in real time, and then people manually has to look through this to come up with this identifying the defects. How to automate this process? So the way we approach the entire problem is a single approach. One is this high fidelity imaging. We don't go with cameras. We need to go with specialized high resolution cameras, and then our CTs, or confocal or laser. The cost goes up as you move along the line, along the plane. And directly, these systems are not meant for doing end of line. So we need to run proprietary algorithms to take the information from the sensor and then modify it for end-of-line testing. So we leverage a lot of sensor signal processing, or we borrow ideas from convex optimizations. Second, the third is we obviously apply deep learning onto these sensor level information, not standard networks, some of the specialized networks. I'll be talking about one of them here. In terms of implementation, we go with edge or embedded implementation, and then obviously we quantize it, or we do a bigger model and then do knowledge distillation. Okay, so I talked about confocal microscopy. In a nutshell, this is one level above the standard fluorescent microscope that you all has seen in schools or inspection process. One difference here is that you can see this focal plane. Now, it works very similar to your fluorescent microscope. You hit the light to the surface and you're basically capturing the reflection from it. The difference is the dichrotic mirror. So in a way, it filters out all the external noise coming out of reflection. So you get very precise capture information of your surface. And also you can vary your focal plane in a way that you adjust all your focal plane towards z-axis, and in a way you can reconstruct the 3D depth. So it's widely used in a fields like bio, where you can see a lot of cell structures reconstructed in 3D. One trivia question, who invented confocal? And he has a link to modern AI, very close link. So anyone from the audience, if you can answer this. Okay, so think about it, Google it, and we'll come back to it at the end of the talk. Okay, all right. So that's in a nutshell. So it's about we use laser for this confocal, and you have this dichrotic to precisely filter things out, and you can reconstruct 3D depth of morphology of what you're looking at the surface level. So we use them and the 3D heights information, which is like a multifocal plane. That forms the information of imaging that we take information out of. So we do a lot of linear or spherical fits for reflectance and luminous corrections. And then basically what we do is that they apply signal processing ideas from here, project this information. So here is your multiple stacks of depth information. For example, I'm just slicing one of the images over here out of this Z plane that we are talking about. And you can't see any information out there with a single plane. But if you combine across all this depth information, then you apply your signal processing. What happens is you basically project this idea into a 2D surface. So now you can see basically, the scratches coming out very clearly, visibly coming out there. So that's our processing chain. You can see you work on these multi-dimensional layer of information. We project them. Then you can see different morphology of defects. In this, you can train any of your object detection model like YOLO or DetectER. Then the implementation will be like, as I mentioned, you quantize and implement it. So that's what we see. In terms of system design, we merge like multiple technologies together, right? So one is this confocal, other is your signal processing, other is your deep learning. How do you rotate the ball? That's the XY staging. You need to precisely rotate it, capture the information. So the idea behind that is that you focus and acquire a single point focus region. And then while you process the data upstream, you rotate the next level, and then you keep iterating this, doing this until you cover the entire surface. So you need to be like precisely handling all this in a system. That's a system design. Current system inspection time is about 8 minutes for a typical 17 mm diameter of ball. So that's the process. So we transition from manual inspection towards a fully automated process. We are achieving about from 6% to 0.3% in terms of defect pass-through, what you are passing through to customers in the sense. Cost of quality reducing to 4%, what we saw about 15 to 20% all the way to a 4%. This study happened like last 2 years of data, what we looked at. Okay, so how much are we doing with timing? So I got 3 minutes. So we look at one more problem, which is your electric motors, e-motors. Starter welding is one of the common problems there, which will typically status is a static part, and then you have these windings and terminals, and you bind them together by these weldings. Typically, these are the common problems that you tend to pick up in this process, very important, which outcomes will be like efficiency or safety recalls. How do we handle that? So the first thing is you mount them with high resolution cameras in a cobot and liquid lens, and then you capture static images of it. Good for obvious defects. You can run any of your object detection models on it, train them, That's the first step of things. Probably the defect pass-through rate will be around 5 to 6%. So not precise enough for a high fidelity precision manufacturing. Then we switch towards 2.5D, that's the confocal imaging I talked about before. So in the sense, you take the snapshot of it and then you can come up with the projections of it to a 2D surface. Then you can train your deep learning models on this 2D surface. It gave us a very good escape rate of 1 to 2% drop, probably about 5x improvement in this case. What I want to cover here is the next level is about the 3D laser points. So what you can extract here is good morphology of information coming out in the sense of 3D point clouds. So you can either use 3D point clouds projected back to a simple 2D surface images, then train your YOLO detection models. It gives you about the 0.1%, but one challenge here is that it cannot differentiate between some of the defects that are reworked or it is inherently basically a defects here. So what we do here is to look at some of direct 3D point cloud architectures. So you can directly use from the laser, these are the 3D point clouds, and these are special neural network architectures like PointNet or PointNet++, that's pretty standard used. There's like two different branches of deep learning evolved here. One is PointNet based, where you directly work on the space, or you take this PointNet and then you transform them to a voxel net. Then you typically train these networks towards this. So this probably achieves us like 0.01% accuracy. Okay, so in a concluding slide, I want to summarize how we saw like expanded imaging techniques where we merged signal processing with deep learning and how we can solve precision manufacturing QC challenges. And I discussed about some of the architectures that merges this like non-traditional technological stacks. Current researchers, like we do multi-samples, are showed about the ball. We're doing like just one sample. And then now we are working on the optics where we can sample like multiple balls together, working at the CMOS sensor level. Second is the point cloud quantization. How do we turn the point clouds and run it quantized very faster, efficient ways? The third is a very interesting area. We call them as physics-informed neural networks, PINN. Some of the optical characteristics can be modeled directly with the deep learning. The network can learn this optics behind it. So basically, this is a very emerging area for research. I'll quickly conclude my talk here. I just want to show one quick video and then wrap up for questions. Okay, so this is the ball inspection I was talking about. I just edited it to 30 seconds. So these are the very tiny 17 mm balls. And you have this confocal microscopy over here. And this is the XY staging. It shows the full rotation of how do you rotate the balls. But you can do this, for example, for 17 mm, these are the number of rotations it takes for you to cover the entire surface area. And you can see this confocal projection of multi-dimension projection of 2D image. And here you can see something with the defect the AI is picking up. Okay. And you can see the status of it in real time. Probably it's doing it, the greens representing no defects, red areas I have some problems, it picked up such defects. Okay, thank you. I hope you have any questions.